So in the last lecture, we have presented vector value functions and established their relationship between parametric equations. In this lecture, we're going to investigate the calculus of vector value functions. So therefore, the concept of limits and derivatives and integral of vector value functions are direct extensions of what you have already learned in Calculus 1 and Calculus 2. The limit of vector value functions in 2D or in 3D is defined much as it is for the scalar value function, which is the regular functions that we learned. So hopefully at the end of this lecture, we could be able to define the limit and the continuity of vector value functions. We again revisit the different rules we can apply to find the derivative of vector value functions, and also we're going to learn how to find the tangent vector at the point for a given position vector, and at the end we're going to calculate the integrals of some vector value functions. So let me quickly give you the definitions of limit of vector value functions and how to calculate the limit of vector value functions. So a vector value function of the form R of t approaches the limit L. So L is the limiting value here and is also a vector. As t approaches a, written in the form of limit of R of t as t approaches a equal to L, provided that the distance between the two values R of t and L, as you take the limit as t approaches a, is going to be equal to 0. So notice that even R is a vector value and also L is a vector value. The distance between R and L is a function of a single variable t, to which our familiar limit theorems apply. Therefore, this definition, together with the following limit, will lead to a straightforward method for computing limits of the vector value functions. So for this theorem, we have three functions, and these are called the scalar value functions, f, g, and h. This function are the function of t. So the limit of the vector value function of the form r of t equal to f of ti plus g of tj plus h of tk as t approaches a is given in this form. That means finding the limit of a vector value function is equivalent to finding the limit of each component of the vector value function. So this limit of r of t is equal to limit of f of ti plus limit of g of tj plus limit of h of tk as t approaches a, provided that the limit of each component exists. In the next definition, we have the idea of continuous functions, or the continuity of vector value functions. So the idea of continuity also extends directly to vector value functions. So a function or vector value functions of the form r of t equal to f of ti plus g of tj plus h of tk is continuous at the point t equal to a if the following three conditions hold. R of a exists, that means a is in the domain of the vector value functions. The limit of the vector value function as t approaches a exists, and the calculations of the limit has to equal to the evaluations of the vector value function at the given point. So we're going to tackle some example, and again you will see that whatever you have learned in Calculus 1 and 2 can directly be applied here. Example 1, so we want to evaluate the following limits. So we want to find the limit of the vector value functions r of t as t approaches 3, given that r of t is equal to t squared minus 3t plus 4i plus 4t plus 3j. So the limit as t approaches 3 of t squared minus 3t plus 4i plus 4t plus 3j is equal to the limit of t squared minus 3t plus 4i as t approaches 3 plus limits as t approaches 3 of 4t plus 3j, when you take the limit of a vector value function, you evaluate the limit of each component of the vector value functions, and all the limit laws that you learned before can be directly extended to vector value function. So that is, to evaluate this limit, you just apply direct substitutions. To evaluate this limit, you also apply direct substitutions. Or you can just apply limit laws such as limit of a sum is the sum of limit of difference of limit of a constant multiple, limit of a product, limit of a quotient, so on and so forth. Again, all the limit laws that you learned before can be directly applied here. So I'm going to use direct substitutions here under the assumptions that the functions that I have are continuous functions. So I got 3 squared minus 3 times 3 plus 4i plus 4 times 3 plus 3j. So this is equal to 4i plus 15j. Or you can write this in the component form as 4, 15. In the next example, you apply the same approach, that is to find the limit of vector value functions. You're going to evaluate the limit of each component of the function. So that is, again, limit as t approaches -2 of square root of t squared minus 3t minus 1i plus the limit as t approaches -2 of 4t plus 3j plus the limit as t approaches -2 of psi of t pi over 2k hat. Then you use direct substitutions. Again, you got square root of -2 squared minus 3 times -2 minus 1i plus 4 times -2 plus 3j plus psi of -2 times pi over 2k hat. Now you evaluate each component of this vector, and you get 3i minus 5j plus a 0k hat, because psi of -pi is going to be 0. And that is the answer for the limit of the vector value function. You can also present this result in terms of the component forms as 3, -5, and 0. So in the next example, we want to consider the functions of the form r of t equal to cosine pi t I plus psi pi tj plus e to the -tk for t is greater than or equal to 0. There are 3 parts to this example. The first part is to evaluate the limit of the function as t approaches 2. The second part is to evaluate the limit of the function as t approaches infinity. And the last part is to ask you to find the point at which the function is continuous. So now for the first part, it's a straightforward calculations. You want to evaluate the limit of the vector value function. What you do is you can find the limit of each component of the vector value function. So limit of r of t as t approaches 2 is equal to the limit of cosine of pi t I as t approaches 2 plus the limit of psi of pi t j as t approaches 2 plus the limit of e to the -t k as t approaches 2. Now again, cosine of pi of t, psi of pi of t, and e to the -t are continuous functions, and therefore you can just use direct substitutions to evaluate the limit. So you got cosine of 2 pi plus psi of 2 pi j plus e to the -2k. So cosine of 2 pi is going to be 1, so the first component is 1i. Psi of 2 pi is equal to 0, so you get 0j plus e to the -2k. So that's the answer for the first part. Again, you can write this result in terms of the component form as 1, 0 e to the -2. Now for the second part, you want to evaluate the limit of the vector value function as t approaches infinity. Now again, you can evaluate this limit by evaluating the limit of each component of a function. So notice that you can evaluate the limit of e to the negative t as t approaches infinity. This is equal to e to the negative infinity, or 1 over e to infinity, so this approaches 0. However, the limit of cosine of pi t as t approaches infinity and the limit of sine of pi t as t approaches infinity do not exist, because sine and cosine function will not approach any value as t approaches infinity. So you say that cosine of pi t as t approaches infinity and limit of sine of pi t as t approaches infinity do not exist, and therefore you conclude that the limit of r of t as t approaches infinity does not exist. Now for the last part, at what point is the vector value functions continuous? Because the component of the vector value function are continuous for all value of t, therefore you can automatically conclude that r is also continuous for all value of t. So for part C, since the components of R are continuous for all t, R of t is continuous for all t. So this is the case where the vector value function is continuous for all value of t. There are other scenarios when you have to find the domain of the function and you have to restrict the domain of the functions to a certain value of t. And if that is the case, then you can have different conclusions on the continuity of the vector value functions. So that's it for limit and the continuity of vector value functions. Now I'm going to move on to talking about the derivative and the integral of vector value functions.